Okay, so now we're into chapter 10, and we're going to be jumping into section 10.2, talking about vector-valued functions. And we're kind of going to just breeze right through section 10.1 because it defines vector-valued functions for us, and I think that vector-valued functions are going to feel pretty natural based on what we've been doing up to this point. So just to put you kind of in that frame of mind, let's think about what we've done so far. If you can hear cats fighting in the background, I am sorry. But recently we reviewed vectors. So there's some v equal to maybe a series of numbers 1, 2, 3, or I hat plus 2j hat plus 3k hat, however we prefer to write that. It's just something that takes an xyz coordinate 1, 2, 3, and it points an arrow to that value. And we also thought about parametric equations. We took that like x equals 3 minus 2t, y equals t, z equals 1 plus t. I don't know. And we could write that in a vector form. 3 minus 2t, t, 1 plus t. And maybe we called that something like r, and it just held on to our x, y, and z coordinates. But this thing we did right here for that vector r is actually a vector-valued function, and we're just going to call it that from now on. So vector-valued function is something we'll call capital F for now, just so that we know we've given it this special name. And it just holds some functions of t, f1 of t, f2 of t, and f3 of t in its x, y, and z components. Just like any function, it's defined over some domain d of time. And it's just going to assign a unique vector that f is going to point to, or f is going to be. For every t we could plug in from the domain. And so I'm going to erase this of time right here because it becomes a little redundant with the way I ended that sentence. And so even if this block of text kind of feels unnecessary to you, that's okay, as long as this definition of f feels intuitive to you based on what we've done so far. And what I'm going to say is that vector-valued functions work like you would expect for f and g vector-valued functions, which I'm just going to write vector functions at this point. You can compute scalar multiplication like we learned for vectors. Across all components of the vector. The sum between the two vector-valued functions only going component-wise. Just like you saw with regular vectors that weren't functions before. And then kind of our vector multiplication operations, the cross and dot product, follow the same formulas as before. So a quick example, I'm just going to let f equal to t squared, t and minus sine of t, and g equal to t 1 over t and 5. Both of these are vector valued functions. It's okay that one component of g is constant. That's still a function of t. Just it never changes. It's kind of uninteresting. And so 5f is just going to be 5t squared, 5t minus 5 sine t. F plus g is going to be component-wise t squared plus t, t plus 1 over t, and 5 minus sine of t. And when you write the vectors with these angle brackets, it's really easy to remember. The components don't mix. So just remember if you had written this like t squared I hat plus t j hat minus sine t k hat, you'd have the ti hat, the 1 over t j hat, 5 k hat. And those components have to match each other for you to add them together. I'm going to keep saying that and it's going to seem silly, but once things become like stressful and time crunch on an exam, it's really easy to make that kind of mistake. So I just want us to always be thinking about it. And then we can do our dot product real quick. F dot g would be equal to t squared times t plus t times 1 over t plus minus sine t times 5. So that's just t cubed plus 1 minus 5 sine t. So all the and I'm not going to do cross product because that takes forever. But all the operations we learned for vectors work the same way, even when we have these unknown values t hanging around. It still follows the same rules. We can also take derivatives and integrals of vector valued functions. So for example, let's take our f. Where's a good f somewhere? I guess we can just use the one we had already. So f equal to t squared I hat plus t j hat minus sine of t k hat. And our derivatives and integrals are just going to happen component-wise. So if we want to compute df dt or f prime of t, however you prefer to write that, that's just going to be looking at the derivative in every component separately. Seriously, what is that arrow? I hate it. So it's going to be ddt of t squared I hat, kind of like all on its own, plus ddt of t j hat plus ddt of minus sine t k hat. Where ddt means I'm just saying, let's take a derivative with respect to t. So that's just 2t I hat plus 1 j hat. Derivative of sine is cosine, so minus cosine t k hat. And this middle step that I did right here, where I kind of wrote the derivative separately for each component, I'm not saying that's something you need to do when you do these problems. I'm just writing it that way so you know what I did. Really, it would be okay if you started here and then ended here. And then let's go ahead and do an integral as well. So if we wanted to integrate f with respect to t, then we would again integrate component-wise. We would say the integral of t squared dt I hat plus the integral of t dt go j hat plus the integral of minus sine t dt k hat. And so that's going to be, 1/3 t cubed I hat plus 1/2 t squared j hat. Integral of minus sine should just be positive cosine plus cosine t k hat. And then one thing you're just going to want to always remember is that you do still have to have plus a constant. But now that constant is going to be a vector. You can kind of see it as really this would have been 1/3 t cubed plus a constant I hat plus 1/2 t squared plus a constant j hat plus cosine t plus a constant k hat. And then that c vector altogether just has your first constant, your second constant, and your third constant. You can represent this either way you want. There's some unknowns that when you take an indefinite integral, that is without bounds, they come out of your integration problem.